We now consider the final form of spectroscopy, which is ultraviolet visible spectroscopy. So earlier in this unit, we have seen that absorption of infrared radiation causes bonds to vibrate, and absorption of radio frequency radiation causes nuclear spins to flip when the molecule is in a magnetic field, which is of course the basis for NMR spectroscopy. Now, certain organic molecules will absorb light in the ultraviolet or visible region of the electromagnetic spectrum. Okay, so just to refresh your memory here, we've been talking in the radio and IR regions, which are low energy. The ultraviolet region corresponds to the region from 200 to 400 nanometers, and the visible region is 400 to 700 or 800 nanometers. Okay, so this region of the spectrum is higher in energy than IR or radio waves, because remember that energy varies directly with frequency, and this region of the spectrum has higher frequency radiation than infrared or radio. And energy is also inversely proportional to wavelength, and the wavelengths in these regions are shorter. Okay, so what happens? Well, if we're in a higher energy region of the spectrum, if the photons that are getting absorbed are higher in energy, the process that has to happen when the molecule absorbs a photon has to be a more energetic process. And that process is that an electron will jump from the ground state to the excited state. Okay, so that's something you've probably seen in general chemistry, having to do with atoms when you excite an atom by shining light on them. But it is also true for molecules. But in this case, what the ground state for a molecule means is that all of the electrons are located in bonding molecular orbitals. And the excited state means that there's an electron in an anti-bonding molecular orbital. In the next lesson, we will have a review of molecular orbital theory so that you can understand what I'm talking about when I talk about bonding and anti-bonding molecular orbitals. So functional groups that will absorb light in the UV invisible region of the spectrum are conjugated polyenes and aromatic rings. Now, you probably know what an aromatic ring is by now, but you may not know what a conjugated polyene is. So the poly just means many, and ene means double bond. So conjugated alkenes, which is a term that I like to use, are molecules in which two or more double bonds are separated by a single bond. So depicted here is the type of such molecules, which is called 1,3-butadiene. Diene for two double bonds at carbon 1 and carbon 3, and but of course means that there are 4 carbons overall. So conjugated dienes behave differently from non-conjugated molecules in 3 ways. So the experimental evidence that there's something different about conjugated dienes is, first of all, they absorb UV light, which is the main topic under consideration in this lesson. But secondly, conjugated dienes are actually more thermodynamically stable than non-conjugated dienes. We will see a couple of reactions as we proceed through this course where the extra stability due to conjugation drives a certain reaction step. And the way that we can tell that something is more thermodynamically stable is we can do what's called a hydrogenation experiment. So it turns out that if you take an alkene and react it with hydrogen in the presence of an appropriate catalyst, it can be converted into an alkane. So if you take 2 molecules of butene and react it with hydrogen, you will get out a total of 254 kilojoules, 2 moles that is. Whereas if you take a molecule of 1,3-butadiene, which has 2 double bonds, but they're in conjugation, you only get out 239 kilojoules per mole. What that means is that the conjugated diene is more stable than 2 isolated alkenes by 15 kilojoules per mole. That may not sound like a lot, and it's not a lot, but it's still enough to cause some differences in reactivity in order to favor this arrangement. Then finally, the single bond between the two double bonds is shorter than a typical carbon-carbon single bond is, which means that it actually has some double bond character. Okay, so if we consider 1,3-butadiene, the double bonds, as you would expect, have bond lengths of 1.34 angstroms, which is right on target with what you would expect for a double bond. But the carbon-carbon bond between C2 and C3, the central bond, which is of course drawn as a single bond, has only a bond length of 1.47 angstroms, which is shorter than a typical carbon-carbon single bond of 1.54 angstroms. So all of these pieces of data can be explained using molecular orbital theory, and in the next lesson we will have a review of molecular orbital theory and a demonstration of how we're going to use molecular orbital theory to study conjugated dienes. Then in the lesson after that, we'll pull lessons 1 and 2 of this section together and talk about how you actually get UV VIS spectra of these sort of molecules.